Alright, and now we are going to continue talking about parameterizations, and just think about how the idea of limits and derivatives work with parameterizations. Alright, so let's go back to Calc 1 and just briefly remind ourselves of how derivatives worked there. When we were first studying them, we had this notion of, okay, well, we have on the xy plane, we have a function like so. Let's call this f, and we said, okay, well, what we're going to do is we're going to fix a point on this curve. We call this x, and then we look at another point over here, call this x plus h1 and the function value it produces, and then we kind of looked at those made a line between them, and that was called the secant line. Okay, then we said, well, okay, maybe we can do a little bit better. We can maybe move to x plus h2, and then we put a point on the curve where that intersects, and then we looked at the secant line there. Okay, and so on and so forth, and eventually we got pretty close to x plus or to x, and eventually what we ended up getting was going from a series of secant lines to tangent line. Okay, well, what about, so that was in 2 dimensions, right? What if we have now n-dimensional curves? Okay, well, let's look at an n-dimensional curve. Okay, and I'm just going to draw one here. Okay, and I'm going to look at this point right here. I'm going to call it, and I should actually name my curve. All right, we have curve C progressing that way. And I'm going to call this point x of t0. Okay, and then, or just x of t, I'm sorry. Let's just call that x of t. All right, and then I'm going to look a little bit later on the curve at another point called x of t plus h, 1. Okay, and again, I can construct now not necessarily a secant line, but I can construct a vector between the 2 points since I'm in n dimensions. Okay, that's fine. And, well, now I'm going to take another point that isn't quite as far along the curve as those as x plus h1. I'm going to take the point x plus and then t plus h2. Okay, and I can construct a vector to that point. All right, fine. And, well, maybe I can get closer yet. I'm going to do this point, x of t plus h3. And if I do that, I can construct a new vector, okay, and so on and so forth, and eventually I can take a series of secant, in quotes, secant vectors, okay, and they are technically secant vectors because they go through 2 points on the curve, and you could extend the t's in both directions as well, and then that goes to our tangent vector. Okay, so same sort of idea. All right, let's see if we can get the algebra to match this idea. So really they're exactly parallel. Okay, so I need to define a vector x and it needs to have n components, x1t, x2t, so on and so forth, to xnt. All right. Okay, and then via the definition of the derivative that I'm familiar with from 2D calculus, okay, so x prime, okay, that should equal, theoretically, the limit as h approaches 0 of x of t, oops, let's try this again, x of t plus h minus x of t all over h. Okay, and then, okay, now at this point, to subtract two vectors, I need to subtract the components. So let's write it out in component form. All right, limit as h goes to 0 of, and then we have x1 t plus h, etc. through xn t plus h. All right, that's the first one. Subtract, and then x1 of t up to xn of t. All right, still all divided by h. Okay, well then according to vector subtraction, I subtract the components, so this is limit as h approaches 0, and then let's see, I'm actually going to do a couple things at the same time. This is x1 t plus h minus x1 of t all over h, etc. through xn t plus h minus xn of t all over h. All right, and then I can actually move the limit inside, so I have limit of the first component, okay, I'm not going to write this out, etc., and then limit of the nth component, all right, which boils down to just saying x, the derivative of the first component, all the way through, in the nth position, it would be the derivative of the nth component. So, bottom line, to differentiate a path x of t, differentiate the components. All right. So just a quick check here. We have the parameterization given to us. We want to find parameterization representing the instantaneous rate of change of the parameterized curve, also known as x prime. All right, x prime of t is, and this is where you pause the video and do it yourself. Okay, this is just going to be negative cosine or negative sine of t squared times 2t, and then this one is going to be cosine of t squared times 2t. And when we differentiate, the restrictions on t don't actually change, so t is still within 0, and then root 2 pi. All right. All right, time to just review some of the geometry that kind of went along with this in the background. We focused on the algebra, now it's time to discuss the geometry. So the vector x of t plus h minus x of t times 1 over h is something actually that's very interesting. So when we were drawing our diagram, we were actually drawing this, and this was the secant vector, right? That was between two places on the curve. But when we multiply it by that 1 over h, it's actually called a scaled secant vector. Okay, so just be aware that the secant vector is just the difference of two vectors, and then that lie where those points lie on the curve, etc., etc. And then when we multiply something, we scale it. Okay. When we found the limit and we said, okay, it was x prime of t, right? That is actually called the tangent vector. Okay, this is the tangent vector. At x of t. Okay. Also, when we're in physical applications, the x of t is typically called the position vector. Okay, position vector. And then this is often referred to as the velocity vector. Okay, and then physicists, just because they don't want to write out x prime all the time, it's literally two symbols. They want one symbol instead. They typically use v of t. Okay, and if we remember from Calc 1, there's also, so if we take the derivative of position, we get velocity. If we take the derivative of velocity, there's acceleration. Just foreshadowing some things. Ooh. Okay. The direction of x prime of t gives the direction of velocity, which we can also call direction of instantaneous motion. Okay, and then the magnitude of this, okay, so just remember the magnitude we use x prime of t and then enclose it in two vertical bars. This is the speed of a particle. Particle at wherever we're at, x of t. Okay. And then, so if we wanted to find the speed of the above curve, we have to do the square root of, and it was minus sine of t squared times 2t, square that, and add that to, and this is just finding the norm if you need to remember how to do that, cosine of t squared times 2t, all that squared. We end up with square root of 4t squared sine of t squared, or sine squared of t squared, plus 4t squared cosine squared of t squared. Lots of squares. Okay, bottom line, what it breaks down to is, okay, pull out the 4t, and then sine squared plus cosine squared is 1. We get 2 absolute value of t, but actually, since t is bigger than 0, okay, this is equal to just 2t. Okay, and that, folks, is the end of this video. We have one more just quick wrap-up video, and then that'll be the end for the videos this week.